All right, so today is the first time we talk about probability. Now, would anybody like to comment? What do you think probability is? What is it that we are trying to calculate? Any ideas?
The chance of something happening.
So to make it more concrete, we are going to toss a coin. It's a fair coin. And I ask, what's the probability that I will get heads when I make this toss? You can hear me, right, guys?
Yes.
So let's a quick wake up. Write in the comments, what would be the probability if I toss the coin that it comes heads? Write in the comments what's the probability, and then we will see. So lots of people wrote 1/2. So you see, you answer this question, but what does 1/2 mean? So we can reason as follows. When you toss a coin, you are creating one of two universes, either universe head or universe tail, correct? So by the number 1/2, you might say that you express the idea that one out of the two universes will come to fruition. Okay, so that's not a bad idea, but there is something wrong about it, because, for instance, you will either live to be 1,000 years or you will not live to be 1,000 years. And to say one out of two, you somehow say that both possibilities are equally likely. Okay, so just to say one out of two, one universe out of two, you will see later that actually ends up being in many cases how we calculate the probability. But you have to remember that it's not just because we have two possibilities, something else is at play here. So this is what, when you think about it, this is what will happen when you perform an experiment great many times. So suppose you toss a coin once, twice, 3 times, 4 times. Let's actually carry out the tosses. You know what I did over the weekend, guys? I actually was tossing a coin. Do you know how many times? 1,200 times, right? I actually did it, right? But I did both things. I did both a simulation, right? You have the simulation, right? So let's toss a bunch of coins and see what we get. If we toss, let's say, how many coins should we toss? Let's toss 10 coins, right? So let's see what happens.
But how long did it take to toss 1,200
We are tossing
times?
10 coins. And we got, you see the blue are the heads and the tails are the reds. Let's see what's the ratio. The ratio that we got is actually exactly 1/2. Interesting. Let's clear the result and toss the coins again. What do we get? My God, what's happening here? It's the first time it's exactly 1/2 twice. Okay, now clear the results. Let's toss this again. What is happening here? I don't know. The software is strange. All right, let's say again. Let's toss. Let's toss 20 coins. Oh, okay, so this time we got slightly different answer. Okay, we got 11 heads. And so let's see the list, right? So you can see you actually have streaks of heads, 4 heads that came at a time, then 3 heads came at a time. Let's clear the result again. Let's toss again. No worries. So look at this, guys. Did you expect? Look how many heads we got here, and strings of them. Let's see the ratio. The ratio this time was 0.7. Yes. So the numbers jump. We'll return to this in a moment. The numbers do jump. Okay, but we expect that nature, given enough many opportunities, will show her preference. What does nature want the outcome to be? How is nature for or against the outcome, 1/2, right? So you think that if you make hundreds, thousands, maybe millions of tosses, then that will really reveal the preference, because you had many opportunities for any of the outcomes, and that's the situation that it will happen. Here is, for example, when I tossed a coin several times. Here I have run 1, I toss coins, right? And this is actually me tossing the coins. You can see that green is where I had heads, and red is where I had tails. And when I toss it another time, I get an entirely different different sequence of heads and tails, right? So we are dealing here with a non-deterministic sequence. Make sense? So the number 1/2, when you say that a coin lands on heads with probability 1/2, what you're really saying is that nature does not care, right? So you would think that if you toss 1,000,000 times this coin, then roughly half of those times it will be heads and half of them will be tails, which means nature has no bias to prefer one outcome to another outcome. Make sense? And that's incidentally, I'm not sure if it matters to you. So what's the worst probability when you ask somebody on a date? The worst thing that can happen is that if she comes, the probability that she comes to the date is 1/2, because that means that she doesn't care at all, right? It's just neither to come nor not to come. If the probability that she comes is very close to 0, that means she does not like you, which therefore means that she is not indifferent to you, okay? Indifference is possibly the worst thing to experience. Good. So here is what we're dealing. That's why I reviewed sequences, right? And that's a very, very strange thing. It's actually more so philosophy than mathematics at this moment, okay? Well, we are going to calculate that the ratio, that's how we are going to measure nature's preference. We're going to calculate the ratio of the number of times we have success. Let's say for this case, for this experiment, how many times do we get heads, divided by the total number of trials. And we take the number of trials to be very large. Large meaning going to infinity. Does it make sense why? The philosophical idea is that one trial, well, there is only one outcome, so you don't know what nature prefers. 2 trials, maybe nature doesn't, still is not enough opportunities to prove what's your exact worth, what's the exact standing of this particular outcome. So we are taking infinitely many trials of the same experiment, and we are hoping that this number will converge. Make sense? And so we're dealing with a non-deterministic sequence, right? Most of the sequences that we tried before were deterministic sequences. Like 1/n is a deterministic sequence. 1/1, 1/1/2, 1/1/3. You know exactly the entries in the rows of the sequence, correct? But here we don't know that at all. So here we're having something that is very difficult to prove, right? So here is just I'm running. Remember what we mean when the sequence converges. It means that the rows of the sequence start looking alike, okay? And here is my sequence. Here is the integers, and here is the actual sequence. So first input, it's 1/1. Second input is 1/2, because we have 1 success for 2 trials, yes? Third input is 1/3, because we had still only 1 success and 3 trials. And as I go down the trials, right, you see what, you understand how the sequence is built, guys. Do I need to explain more? 8/20 is for the 20 trials. This is how my row looks like, 8/20. Okay, this is still, you see, not, I haven't run the sequence to infinity. To verify the true nature of this limit, it seems I have to run it to infinity. I have to see that the columns here will tend to 1/2. 8/20 is 0.4. Now I do the same experiment again. So I call it run number 2, and I have an entirely different sequence. This time it ends up being actually a 20th row, exactly 1/2, but it will possibly change on the next trial. So finally, many trials do not communicate the whim of the universe precisely, right? Perhaps you might say that they don't communicate it at all, because the sequence is non-determined. Before I run the experiment, I have no idea what terms of the sequence will I generate. But notice what happens if I increase the number of trials to a large number. So I'm just looking at some select rows, you know, because you cannot draw 10,000 rows. I don't want to do that. So let's see if I have the experiment. I try to run the experiment, and the experiment means many trials, infinitely many trials within each experiment. I run it 5 times here. So let's say what happens if I have this experiment and I look at a row number 10. That means I threw the coin 10 times. On this trial, I got 0.5. That means exactly half of the throws were heads. Here I had 0.6, here I have 0.8, 0.7, 0.6. You see variety, right? They are not the same entries at the 10th place. When I take 100, then the diversity begins to be reduced. The rows look more and more alike, okay? So they are not the same, but the entries start looking more alike. When I do 1,000, they look even more alike. And when I do 10,000, look how much like 0.5 they appear, you see? But it seems that convergence of this limit might begin to occur around 10,000 throws of the coin. Understand? Well, it depends, of course, what you mean, but within how many digits, right? So this is pretty close to 1/2, maybe with epsilon equal to 1/10 to the second power, perhaps, right? So there is a difference of the second coordinate here, right? So 1/10 to the minus 1/10 to the power of 2 seems about right. Good. All right. So all these observations do to us, and it leads us to this again to be more convinced of this idea that when I run the sequence finitely many times, there is a diversity. But as I increase the number of runs, the rows of the different runs start looking alike. Okay. And when I increase the trials to infinity, they will all converge to the same number. This is a very, very strong requirement. Notice with the sequence, that's the informal definition of probability that I'm giving here. You will say that an event A has probability P of A, which will be definitely a number between 0 and 1, when this limit converges. You understand? When you see how many times does the event A occur, divided by total number of trials, will show you what is the natural preference to this limit. Good. Now, I hope you do understand how difficult it is to be convinced that this limit exists, because you need to run the experiment infinitely many times. You see, each trial is one experiment. You have to have infinitely many trials, and then it seems you have to verify it infinitely often. You have to verify that every time you do this experiment, you will have the same outcome, the same limit. So even if you could somehow construct a column containing infinitely many entries here, leading to 1/2, that doesn't mean that when you do the experiment again, when you try to replicate it, you will get again 1/2. So you have to be able to verify it. So basically somehow claim that this limit is 1/2 on every occasion. Okay, not so that it involves running it to infinity. Okay, so that's why I think probability is extremely hard to grasp, right? Is that do you believe in such a limit? Do you believe in such that's such a thing where we have no obvious tools to calculate it, that it will exist? Right? Well, are you with me? Do you understand what I said? I'm somewhat in another word a little bit, but I hope it is affecting you, right? It's pretty interesting, right? To wrap your mind, what is it that we're trying to calculate? So would anybody comment? How would I know that that probability of throwing a coin is 1/2? Since I cannot execute. You see, this is just a simulation, and this does not prove anything. It just proved that for the five procedures that I conducted, by the time I throw the coin 10,000 times, I approach, I have a number that kind of looks like 1/2, but kind of is a very vague thing, right? There is no reason why, if I were to repeat those experiments millions upon millions of times, there will be, of course, it's possible that even at the 10,000th entry, the number is very different from 1/2. It could deviate extremely. It could even be as high as 1, even though that's very unlikely that you will observe it. You see, you understand what I'm saying, right? So the idea of this 1/2, at least as far as I described it right now, means that you carry an experiment infinitely many times, And still that doesn't prove, even if you could carry the experiment infinitely many times, that does not prove that the number is 1/2, because if you decide to do it again, maybe the second time you run the sequence, it will generate different values and therefore a different limit. So why do you believe that a coin has probability 1/2 of landing heads? As simple as that, I'm asking you guys.
Because there are two options that equally likely
I can hear you,
to happen.
You're speaking, but no voice is coming out. Okay, Sayed, there are two sides and two possibilities. That's what we began with, but look at that, right? So that's an excellent starting point, but you are making a terrible, dangerous proposition here, right? When we are tossing a coin, one of two universes will be created. Either universe where we have heads coming out, or the universe where we have tails coming out. By the way, guys, again, for whichever reason, internet here begins to, not be too nice. So let me know if my sound and everything is coming through, okay? Or stop me and ask me to repeat if something fails. Two sides, two possibilities, and here, guys, right? So that's why some people say 1 out of 2, because they say two sides, two possibilities. But then in other words, when you say 1/2 comes out, sorry, head comes out, it's one universe out of 2, 1 out of 2. But you will not say that your probability of living to 1,000 years is 1 out of 2, correct? Because you also have two possibilities. Either you live to be 1,000-year-old, or you do not live to be 1,000-year-old. They are not equally weight possibilities, okay? So you see but that's the problem, right? It's a huge claim, right? You are not going to throw the coin infinitely many times, and even if you throw, that's what I call round one. You imagine trying the experiment where you throw the coin infinitely many times, so that's that will generate somehow 1/2, even if you could do that. But then you try to replicate it. Somebody else says, I don't believe you. Maybe if I do it again, I'm generating a different sequence. You see that here is one sequence and here is a different sequence. It's a non-deterministic sequence. Why would it necessarily converge to the same value for the second time? And even if I verified it converges to the somehow, after doing twice infinitely many procedures, if I verified I have convergence to 1/2 twice, that still doesn't prove, because I can do it 5, 6 times, or maybe at a different time of the day. You understand? So that's what I'm asking you. What is it that makes you convinced that a coin lands with probability 1/2, right, without doing this procedure? Anybody wants to say something? Or all right, I'll tell you what I would say about it, right? So very simply, because I am already convinced that nature has no preference for one side to another, right? So in some sense, I'm the advocate of the universe, and I'm saying there is absolutely no reason that I can foresee that nature will prefer one side to another. I just have a feeling, you might say, subjective if you like, maybe not subjective, that there is no preference, right? The best I can verify is that if you do toss it 10,000 times, then the answer is close to 1/2, and that's an approximation. Everything you do with experiments, that's why it remains to be a theory. You never say that Newton's law is a universal truth. You don't say Einstein's theory of relativity is a universal truth. You call it a theory, because what it means is that to the best of your current knowledge, you have not been able to disprove it. You have to remember that. Nothing that you know about our life, our universe, is absolutely set and certain. Yes? Why did you disappear from me, guys? A lot of you were around and you decided to avoid your gaze. Yeah, here you are. Good. Okay, makes sense? So this type of thinking is we're going to define probability axiomatically, but then it loses all relation to the real world. I can say something with absolute certainty, but then I do not know what I'm talking about. I have no idea what it relates to, or I lose some certainty and yet have this sense of what it is, perhaps, right? A feeling of what am I talking about. That's a trade-off, right? So you can make something absolutely true, but then it's abstract and possibly unrelated to the thing that you were investigating, or you can sacrifice that and make it more intuitive. Okay, so that's this type of reasoning, the sequential reasoning will be the way I will establish some formulas. For example, that's the way I will speak about expected value, which hopefully will make sense, expectation, and about about conditional probability in chapter 3. All those ideas I will speak in terms of the sequence. It's just I imagine it converges, and then I can derive a lot of results. But I will also present, possibly today, the axiomatic approach, okay? So let's try to understand how that limit is going to work. Here is an exercise, guys. Are you with me? So you are betting on boxer A to win against boxer B, because you're saying that boxer A is twice as good a fighter as boxer B. What is the probability that you will win the bet? Do you understand what I'm asking? So boxer A is twice as good a fighter as boxer B. In other words, he's twice as likely to win as boxer B. Okay, 2 people right away came with the answer, and that's very nice. But I want you to do it for a moment slowly to think about it in terms of the limit that I presented. Are you with me, guys? Yes, Shotaro. Good. Let's see how we do that using the limit, or do you still want to work on it, guys? Let me know if you want me to proceed. Type in the comments, okay? Sure. Okay, somebody asked a little more time, so I will wait 2 more minutes. Okay, guys? And don't be afraid to be loud. I see I'm speaking, it's so quiet. It's eerie quiet. Okay, guys. 1 more minute and we'll go on. Great, Chabeli. Glad to hear it. So here is how we can go through the limit. So yes. So here is the idea, guys. So when I say that boxer A is twice as good a fighter as boxer B, I'm assuming that nature itself has told me that. And what does it mean? It means that if you are allowing enough chances, in other words, if there are many matches between boxer A and boxer B, there is no certainty that there is a victory, right? And we're assuming here that there is no what do you call it, there is no match, right? So it's not like it cannot end in a draw. So either it ends with a victory for A or a loss for A, or a victory for B. That's the same thing, right? So what we have here is, suppose we played many matches. Some of those matches, and A of them were victories of A, and then B of them were victories for B. And if I run huge many matches, I'm not sure how many, it depends on the particular rate of convergence. So for example, you see, that's why I played it for the coin toss. It appears to be quite good once I have 10,000 tosses, possibly extremely good when I have 100,000 tosses. Okay, so I'm not sure how many matches I have to run to see that that NA will roughly equal to 2 times NB, because this guy has won twice as many matches as the second guy. Make sense? A wins twice as many matches as the second guy, and so I have this limit. Probability of A is limit as n goes to infinity, and A over n, which I can denominator can always be written as NA plus NB. That's always true, no matter how many n's I had here. You understand why? Because some games go to A, some games or some matches go to B. And so what is this guy on the top? He is twice the number of B. And here I have twice the number of B plus B. And here I can just simply cross out the NB. I can cross them out and I am left with 2/3. Are you with me, guys? You understood how I got 2/3? Some of you got it way before I even said anything, but you understand how I got it using this limit. Type yes, or if you want more explanation, guys, again, don't be shy. If I appear that I know what I'm talking about, you're deadly mistaken. I have no idea. Grasp it, guys, right away. What is it we're talking about? Okay, let's move on. So, do you know ABBA's song, "The Winner Takes It All"? It's a song about probability. If not, I definitely have to play it for you. How many of you know the song? Write in the comments you know it. And you don't know, Chabeli? So those that don't know it, I will have to play. Should I play now? The thing is, I have to pause the video to do so, because I have a feeling that YouTube will suspend this video once it's posted if it's in it. Okay? Do you want to hear it? Okay, let's hear it. All right, I'm pausing the video and I will restart the video once the song is played. Ready? And back to the lecture, guys. So now that you know this song, now that we know the song, let's answer this question. What does the line, by the way, they're Swedes, you know, Swedish, right? What does the line, their minds as cold as ice means? The gods may throw a dice, their minds as cold as ice. So what does it mean? They are. But when you roll the dice, what is that? What's the word? Mind as cold as ice means they don't care. They have no preference for one outcome or another. Knowing this information, tell me what's the probability of getting, let's say, the outcome 1. And calculate it, guys. Calculate it using this limit just to be sure that you understand why that. Because you remember you did it in elementary school. It feels to you almost obvious. Why is it 1/6? I want you to tell me. How is it, Malika? Makes sense what I'm saying so far? I'm very glad. You know, guys, as I mentioned, I will try to do it soon. Gambler is a good book by Dostoevsky, which you might want to read for this class. Because there are 6 sides and no preference, yes. So let's see that in a limit, guys. Are you ready? Or do you want some more time to work it out? Okay, cool, ready. So here is why it is 1/6 based on this idea, right? We pretend that we know that this limit is going to be already, well, nature has already determined its preference. So what are we seeing here? So how many times do we get the number 1? It should be, if n is very large, well, n is going to be the sum of the outcomes. Some of the outcomes will be 1, some 2, some 3, some 4, and onwards. But when n is very large, we expect, that's how we know nature has no preference, is that if I gave many opportunities for many outcomes to appear, roughly each outcome appeared roughly the same number of times. Make sense? That's what I mean by this somewhat equality. Right? They don't have to appear exactly the same number of times, but roughly similar. So then what happens is this. So I have that n1 over n. It's n1 over this summation, but the summation where n is very large is just 6 times n1 because they are all essentially the same. So then I can cross n1 and I'm getting 1/6. Okay. We will again describe the situation. So some people reason as follows, as I mentioned again, they say 1 is 1/6 universes, right? So there is a 1 and there are 6 possible universes. 1/6 is therefore the answer. But that is only true if there is no preference to one universe over another universe. So be very careful. Here is the first question that possibly is extremely interesting to you. If the probability of an event is 0, does it mean that the event cannot happen? Think about what I'm asking, guys, right? So I say the probability is 0. The probability you get your favorite toy is 0. Does it mean you don't get your favorite toy? Well, when we talk about probability, means again, you see, it's a somewhat idea. We imagine running infinitely many experiments, right? Because every time you run finitely many of them, that's just approximations. That just you're saying, well, based on the theory, we predicted the number to be, let's say, 1/2 for the coins. I tossed it many times, and the number is close to 1/2. So you use this idea that it's close to 1/2 to be strong evidence for the possibility that if I were to throw the coin infinitely many times, I will get 1/2. You understand? So it's a plausibility evidence. It's not certainty by no means, right? Because you can throw more and maybe the coin will start showing different preferences. So here is an interesting example. I hope you will understand it. Okay. It's called, I'm not sure, you are sitting there in your houses. I'm sure you try to order food online, correct? Through Uber Eats or Seamless and whatnot. So when you order something, you see that delivery is estimated to be between one moment and another moment. For simplicity, I will say that, let's say the delivery is estimated to occur between 12 p.m. and 13 p.m. or just 12 and 13. I'm not sure what you call that. Okay. Strictly speaking, because you understand that this is a limit, guys, remember that this limit can go to the number 0, even if the numerator is not 0. The numerator can be finite or just growing slow enough for the denominator to crash it to 0. If you studied limits from calculus, you realize that limit has a possibility of converging to 0 without actually always having the terms of the sequence equal 0. So back to this problem, right? So here is, I try to come up with one that that will be believable to you. So the question is this, right? So the delivery problem, what's the probability? Give me any moment of time, right? Let's say, what's the probability the delivery man will come at 12:30 or any other moment of time, right? So I'm going to show you that the probability that the delivery man comes at any moment of time between 12 and 1 o'clock is 0. Do you understand? I'm going to try to show you. I hope you will be convinced by that argument. So assume that the delivery man has no preference when to arrive. He will come, he is equally likely to come in any moment of time. You understand what I mean? So there is no preference for any specific time. It's not like he is hurrying or trying to be tardy. Okay? So here is what we can do. So we can make it a discrete problem. Well, in later chapters, we will learn more to understand it. Let's just approximate the situation. Suppose that we divide the time interval into 6 segments. Guys, what's the probability he comes in any one of those 6 segments? You understand? I take the time. There are so many moments. There are infinitely many moments between 12 and 13. So let's suppose I divide the interval into just 6 segments. What's the probability that the delivery man arrives in one of those 6 segments? Please type your answer. Wonderful. Kazi, say, okay, one person said it. Milika says 1/6. Wonderful. Now, if I were to divide the time interval into 30 segments, or let's say let's do 100. Divide the time interval into 100 segments. What's the probability he will come in any of those 100 segments, in any particular 100th segment? Can you imagine, right? The interval, exactly, Chabeli, 1/100. But those are artificial divisions, right? So I can divide the intervals into 1,000,000, right? And the probability will come in this millionth segment is 1/1,000,000. Do you understand? And in general, what I do is I can estimate the probability by dividing by n segments and then pushing n to infinity. You understand? So the probability will come at exactly t0 for any time that you mention. You can say 12 a.m. or 12 p.m. or 12:30 or any time that you prefer. Mention it. Call it t0. I'm just showing that at any moment t0, the probability that your delivery person will come then is 0. Do you understand? P of t0 is 0 for any, I'm just talking about any particular moment of time. You understand what the variable t0 here means? So I showed it 0. Can anybody try to explain to me what happens here, right? So doesn't it mean that the delivery person will not arrive at any moment of time? That the moment of time where the delivery person will come does not exist? You understood my argument. I tried to make it as simple as I possibly could at this stage, right? Just the probability that the person comes to deliver your food at a particular exact moment of time is 0. Yet experience tells you that the delivery person will come and deliver it at a particular moment of time. Yes, but that's geometry. Why isn't the person coming to deliver your food? He says he will come between 12 and 13, and he actually comes. So there is actually a moment of time where he arrived. But you just said that for any moment of time, you just proved that for any moment of time, the probability is 0. How do you explain what happened? Yes, possibly, but what does it mean, Shotaro? So you roll a dice with infinitely many sides, but so what does it mean that the probability is 0? Yes, but what would you interpret in this if you run this experiment? If you try to run the experiment, for success means arrival at t0, failure means not arriving at t0. What would you observe? So if you run this this non-deterministic sequence, this probability limit, what would you observe, do you think? You understand what I'm asking you guys, yes?
Well, Professor, if you like roll a dice with infinitely many sides, like it will land on one side, but since there are so many possibilities, it's like, you know, it's close enough to zero if you take the
Yes,
limit.
well, what you're saying is then pretty good, guys, right? So what you will observe is either for that time that you noticed, either it never occurs, so you run it infinitely many times again and again and again, and it never occurs, or it occurs, let's say, once. Let's say if you notice that you will never guess the time at which you will arrive. You see, if you give me a time at which you will arrive, you will never actually observe the time, okay? But let's say you do this experiment in this way. So you play, and then you notice when the person arrives, right? The moment when you arrive, then you pick that time. That is going to be the time I'm going to use. And then if you play this experiment again, you just restart it and record the event, restart it, record the event. You will never see a repetition, you understand? So if you actually observe a particular time, the time will not be repeated. So the limit will be zero. So the sequence that here, it is repeated, you see? Here I have heads 1, and then you are guaranteed that if you roll it again and again, you will have more heads. It will happen more than once, right? But with this new experiment, you will have at most one situation where that moment of time appears. If you actually take a moment of time before observation, or before observing when a delivery person arrives, you will not guess it. In other words, I can bet that this is going to be entirely red. No matter how far you go, it's going to be a red column. Okay, and no success is observed. Or if you cannot see when you arrive, then you'll begin playing this experiment afterwards. You might see it once. See, you understand what I'm saying, right? So it's that type of experiment where successes don't repeat because there are just so many possibilities. So that's one easy example of where something has probability 0, and yet it can happen, and it does. You know, some outcome will happen. It happens without any repeated frequency. So I bet you didn't know that. I mean, maybe what I said before, you kind of possibly had some hunch about probability, even though I doubt it, because I can tell you that if you ask me again, I do not know what probability is, right? I just pretend that I do. I have this type of philosophy that I think that it's pretty vague, but I can construct formulas on top of it. And that also gives me some problems interpreting the results of probability. You see, for example, if you say my probability of success is 1/2, right? I do not know what to do with the number because I'm not going to actually attempt infinitely many trials. I attempt it once, you understand? And the limits are just indicating convergence. So I have to have a sense of how fast it converges. Usually when you apply probability, you have a sense that, that each experiment is exactly the same, and therefore on average, the outcomes repeat with equal distance among them. You know, successes have an equal distance among them on average. Which again, look at the outcomes. By the way, did you ever think that a fair coin, that's actually me tossing a coin. I did it, I told you, 1,200 times. I didn't toss one coin 1,200 times, but I tossed 20 at a time, okay? So look at it. Would you believe that you could observe such an outcome? I wonder. Most people, when they try to pretend that a number is random, they whatever is random does not seem random to them. You understand that? True randomness that does not seem random to people, because look at it. Look how many I had 9 consecutive failures. I'm sorry, 9 consecutive failures, and that happens. How often do you think that happens? Think about it. If you say that a coin is it's a fair coin, that will be 1/2 times 1/2. It will be 1/2 to the power of 9. And that's a pretty small number, right? But yet it happens frequently. That's something you should want to think about. Do you understand what I'm saying? So if I just begin tossing the coin right now, and the probability that I will write from first toss to the 9th toss, they are all going to be tails. The probability is 1/2 to the power of 9. Yet it's not actually not too rare to see consecutive runs of tails like what I did over here. We're going to talk about such things later in this course. That's why you see, so some people might think that this column is not randomly generated. So most people, when they do randomness, they probably do heads, tails, tails, heads. You know, they don't allow for long runs. You see, most people don't like to see the same result repeated many times. They think, oh my God, I'm being biased, so they switch. But actually, that's how randomness looks like. You can play that game. I can send you the link. You can play and see simulations. You don't have to toss the coin if you believe the software, right? Because for Neumann, another person you should listen about is, you know, he said that you cannot simulate through randomness, right? Whatever is in the computer, it's an artificial type of randomness. Okay, so where are we? So we figured out that probability 0 does not mean that there is no chance of this happening. I hope you agree with me. Now the next question, possibly you will answer it very fast. If the probability of something is 1, does it mean that it always happens? So the probability of an outcome is 1. Does it mean that the outcome always happens? What are you thinking about, Stumped? Give me a moment, I need to remove a problem. So just like with the previous question, if you take it to mean a limit, if you understand that probability is a limit, you should expect it's not always going to be the case. Here is a simple example, right? So take the previous question with the time, right? With the time of arrival of the delivery guy. And you can eliminate any countably many points. You can eliminate one moment of arrival or even infinitely many of them, even as infinite as the collection of rational numbers. If you zoom in anywhere, you see rational numbers. With probability 1, the delivery guy will arrive at another number, you understand? So the numbers you remove will not affect the arrival. With probability 1, it will be arriving not at the number you removed. And yet it's possible to arrive at those numbers. You understand what I'm saying? So probability 1 also does not mean that something happens always. It just means that the limit the opposite thing happens rare enough that it will not affect the limit. It happens finitely many times or rarely enough not to affect the limit. Make sense? Why do you think otherwise in your daily life? Because you use experience. You understand? You use experience. You are estimating probability by running finitely many trials, correct? You're not going to have time to run infinitely many trials. You cannot do that. If within finitely many trials you have one failure, then the ratio is already less than 1. You understand? So the probability is not 1 based on your finite truncation, on your estimation. Okay, that's why in your daily life you think if probability is 1, it's always happening, because let's say if I run the experiment only 100 times, the only way to get the ratio equal 100 at the very equal to 1, sorry, at the very last row, is to have everything a success. You understand? Every trial has to be a success. If I run it to even 100,000, you understand? Even 100,000 trials, probability is 1 only for the truncated version, only if every entry is success. But that's not what we think. Ideal probability is taking the limit to infinity. Can you still see me? It says the internet is unstable. Am I not cutting off? Going through? Let me know, guys. Okay. Sound has been breaking up a little. Okay. I hope so. Okay, guys. So here is my next question. Could there be things that do not have probability? Are you with me? And not having probability, it's not having probability 0, because the probability 0 means event is extremely rare, doesn't happen frequently, or doesn't happen at all in ordinary speech. Because in ordinary speech, if you observe an event happening, you think the probability isn't 0, because you only, let's say, had even 100,000 or 1 million observations. One successful outcome makes probability very small, but not 0. You see? Because you don't go through the infinite column. But true probability is taking the limit. So do you believe that there is something where probability doesn't exist? Or does it sound unusual to you, or scary, or strange? Hmm? Well, every time you run finitely many experiments, you haven't established that probability is there, right? Establishing is a very strange thing here. So the limit might not exist. Here is my example of what I imagine. I try to come up with a simple example. It's a bit contrived, but there is, let's say, something known as non-measurable sets in analysis, and those are sets that have no probability, okay? But let me give you a much simpler example, okay? So imagine we have this machine. This is how I'm going to simulate. And well, Abhishek, thank you for your comment. Impossible event. Impossible event, I think if you interpret the word impossible, means it cannot occur, okay? Impossible cannot occur, and if it cannot occur, the probability is 0, right? If something cannot happen, the probability of that happening is 0, right? An impossible event is one that can never be successful. But something that does not have a probability must be very strange, okay? And here is my simple attempt to simulate what it would be, what would be an event that can happen, but has impossible probability. In other words, does not have a probability. Limit does not converge, okay? Or at least does not converge to the same value every time you turn on the event. So here is your machine, okay? Your machine is your universe. Alien coming to your apartment tonight, well, that can happen, right? That either has probability 0 or probability 1 or something in between, right? It depends what you think is alien. To me, every person is an alien. So that is not something that probability does not exist. It's different, okay? Alien coming to your house might be, you'll say, well, I don't believe it will happen. That means probability is 0. Okay, that's an event that has probability. No, probability events that do not have probabilities are somewhat stranger. Okay, somewhat even more scary, right? So if you truly want to be horrified, think about things that do not have probabilities. Right? Think of Solaris. You should all read Stanislav Lem Solaris, and there is also a movie by Tarkovsky. Right? I can send you a link to that movie. That's good that you did, right? So you watched but you have to understand there was an American remake, and that's crap, and there is the Russian original, which is great. although graphic department there wasn't. I mean, it's a brilliant movie. Really think about the beginning of it and the end, connect them two. Okay, Solaris, you know what it is about, guys? So you fly into a far off place. There is this strange planet, and the reason it became interested is that this planet changes its orbit in a very artificial way. And so they started thinking, the scientists, perhaps this planet is alive. Okay, it's some sort of a form of intelligent life. But whenever they go there, it is so perplexing to them, so beyond their understanding, that most people just go insane. Understand? And the people there, many of them commit suicide or have some nightmares or something strange is happening there. There's both movie and the book. It's a bit different. Okay, the book is by a Polish writer, and the movie is there are somewhat two different concepts, both very interesting, right? And there is something that sends chills at the back of my spine, right? And that is, it's not a horror movie, understand? And that's something that you will notice if you watch the beginning and the end of it, and of course possibly the in between, okay? But the beginning and end of it, right? It's something that I have a similar feeling when I think about non-existent probabilities. So here is the experiment that I came up with, and be my guest and critique it if you think you don't like it. So my universe, I first will turn the universe on. The universe is this machine. I press on, okay? And once I press on, the machine will flip a die. Sorry, would flip a coin. And the outcome is either heads or tails. You understand? Every time I start the universe, it will be either heads or tails. And then when I press start, that's when I perform the experiment. And when I press start, what will you have, right? When I press start, I will observe the following thing. I will observe either only basically the machine is going to basically replicate heads, or just print that that it's in a state of yes. So 1 second, you see there is a very, this is one problem that I always try to remove. This problem is well, it's a blight, right? Since my brother brought it home, it does not let me leave, destroys on purpose, mind you, not because it's stupid. It's very not stupid, right? Here it enters the house again because it can open doors. And no, this cat does not want love, Melissa. You're quite wrong about it. This cat wants something else. It's blackmail, right? Oh, it's actually a blackmail, but what it wants to do is blackmail me for food. And what it does, let me tell you, it knows the things that I love, the things that I work on, like my books, and it will start chewing them if I don't give it what it wants. And it tries to break the screen. In other words, it hits the screen on purpose so it falls and looks at me for a reaction. And that's how the cat is getting more food than it's supposed to, right? It wants to get diabetes. I can show you, right? What it does. There's a video what it does when I work on the mouse, for example. It bites me on my fingers. Okay. So yes, anyhow. Yes, attention. So again, right, what I do is I call it, by the way, you don't know it, you know what's a paddle, right? Only if you speak Russian, I call it launching padla, right? Just when you throw it out, it means just launch a piece of, so I pick it and I toss it like a torpedo. It will keep it. Actually, also have a gun, right? I show the gun at what's up, right? And when he sees the gun, he goes and leaves for a moment. Afterwards, it comes again. It's a Nerf gun. Anyhow, so back to this particular problem. It is a very bad word, right? So yes, exactly. So here we turn on the universe. The universe will then be in state H or state T, and then when I start performing my infinitely many experiments, okay? And then what I have is either head or TTT, right? So notice if I record the limits, I will either have the limit is in some of my runs I will have that the limit is 1, and in other runs I will have that my limit is 0. Do you understand what I'm saying? And you might say, well, any critiques, guys? Before I continue, do you have a critique of my experiment that has no probability? Do you understand what I mean? Experiment is pressing start. And then there is this thing that the universe changes its mind. You understand? When something has no probability, it means that the universe is somehow changing its mind. You see, what does have a probability is that the universe will produce an infinite sequence of heads or an infinite sequence of tails. But what does not have a probability based on my setup, I think, is that the universe will produce, the probability it will be heads. In other words, the probability that we have heads, it does not exist, but the probability that the universe will be in one state or another does exist here. Are you with me? Hello, guys. So yes, but you're not here with me in your spirit, right? I mean, I just look at it, I tell you, this is my invention. I'm showing you a situation, a universe that produces no probability, understand? The thing is, the problem is you might be bothered about who presses the on and off, but imagine you're a creature living inside of this universe, right? And, you know, at some moments I decide I am God, you know, I have, once you're alone, you have those ideations, you know, you lose your mind, you start thinking you're Napoleon or God, nobody visits me, grandchildren don't come. So yeah, so then somebody decides, the God decides to press the button on, right? And when the God decides to press the button on, the scientist living inside of this universe tossing the coin sees something extremely weird. He says, okay, I'm tossing this coin. Oh my God, I do it even infinitely many times, or I mean, a huge number of times. And I see that this time, this experiment, my colleague, I just concluded that where I found this magical coin that always lands on heads. Yes. And then the other scientist is going, okay, I'm going to check your experiment. I'm going to do this experiment again. And he begins tossing this coin and he said, my respected colleague, but what are you talking about? Heads never comes up, right? Look, I run a million simulation running the experiment 1,000,000 times, yes? And then the first scientist gets very upset. I mean, come on, look at my procedure. Everything was controlled here. I toss this coin all the time, only heads, okay? So that's something that might happen in Solaris. You are hard to please, guys. If you so any critique of what I just said, any comments to it? Maybe you don't agree that my experiment is good, or a good demonstration that probability may not exist. To me, actually, it's strange that probability does exist. Or when people say, what's the probability of something, sometimes I find, how do you know anything has probability, truly? No takers?
Anytime you hit start, it just switches between heads and tails, or is it just random?
Well, it's in some sense it's random. You understand? So you as the little scientist, you can press start. Okay, so start is basically what it means. You start flipping the coin. Okay, but the universe or God or whatever you like can turn on, right? Can press the on button. When I press the on button, right? Let's say I am nature. I can press the on button. Okay. If I press the on button, there is going to be a random event, either heads or tails. Okay. And then that will be determined. And then this guy will only be basically he's having this coin, but I have some interesting control over it. You understand? You have the coin. It has two sides. Okay. Living in this universe, I'm trying to imagine what the universe looks like. So if I live in this universe, I see a coin that has two sides, heads or tails. Okay. Now I begin to throw it, right? So when I begin to throw it, somebody else, some other creature or nature, right, looks at me. You know, nature can be very cruel. You've seen National Geographic. So it presses on, the button on, and then what happens as I throw it, it only lands on heads or only lands on tails. You understand? I toss it, I toss it, I toss it, and I see that the coin is only producing heads, nothing else. Even though it has two sides, somehow no matter what I do, it's always heads. I toss it, my God, it's heads. I did it 100 billion times if I could possibly do it so long, right? And it's always heads. And then I conclude this is a very strange coin. Right? I go to my other colleague and I say, okay, can you try that? And he begins doing the same thing. And he sees that the coin is only generating tails. Right? And it just behaves in this very weird way. You understand? Only heads, only tails. So the limit, my point is the limit does not exist. So you see, you do not have this repetition. You see, this is one person doing the experiment, tossing the coin, another, a third, a fourth, a fifth, right? When they do that, they don't agree about the limit. The limit is not the same.
Oh, okay.
You understand what I mean? It's not only that you have to carry the experiment infinitely many times or infinitely many repetitions of it, you also have to have the same result replicatable. So experimentally, it's impossible to demonstrate according to those conditions what probability is, you understand? It's just the reason that we can conclude about certain things. We begin modeling probability based on some phenomena. We can say that, well, it does not, we don't imagine that somebody presses the button. At least we had no evidence of that happening. Maybe there is somebody pressing button, right? But we don't have evidence of that happening. In other words, we can toss a coin. You can toss a coin. You can definitely do that. It's very long, but you can do it 10,000 times. Okay, if you toss many coins at the same time, and you note how many heads we have, somebody else does it, and we can generate a huge body of evidence, and then all of those numbers look kind of like 1/2. So they seem to indicate that this theoretical limit, which I cannot verify, exists and equals to 1/2. You understand? And this thing is back.
So like if the experiment can't be replicated, then
well, you cannot perform. What is the experiment? An experiment is tossing the coin once, but you get this 1/2 for the coin if you toss it many times. Actually, when the number of times you toss it approaches to infinity. Yes. Are you with me, guys? Do I believe Bowen? Okay, so now we have interesting questions here, right? What do I believe in? Free will? I do not know what free will even means. That's the problem, right? How can I believe in free will? What is that? I understand determinism. Determinism means that, in theory at least, if you could note the motions of every single particle, of everything around you in this universe, if you could take a note of that, then in the future and in the past, everything is entirely predictable. Okay. By the way, which is another thing. Predictable is an ability to interpret what that future will be. It might be determined and unpredictable. Okay. Or if you have probability, it's something that is very wanton. It's very, I cannot come up with an English word, launish, which means moody. I think, yeah, moody. Okay. Something very moody. That's when the coin, right? Well, I don't know. Maybe I wanted to be head. Maybe I wanted to be tail. Even though when you actually toss a coin, it's mechanical procedure, right? It's like you toss a coin. It's already determined what it will land as. Okay. It's just the probability part comes from uncertainty, that I do not know in what position the coin was, so I can just use this limit and predict it's sometimes head, sometimes tail, and it will be 1/2 because the procedure does not prefer one side over another. Okay, that's why I can think of probability. But yes, on a micro scale, possibly, right? In some theories, it says that this randomness seems to be principle. You understand? So if the particles are tiny, 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 then they behave on probability principles. And determinism on a macro scale is what you call expected value. We're going to talk about it, right? So why half-life happens in such a predictable way? It's because it's a macro scale. Each atom can decide to blow up anytime it feels like it. There is no reason to it, possibly fundamentally no reason for it to decide to disappear, to blow up. Okay, and release alpha particles. But the expected value is deterministic, because the expected value, you have millions of particles. They will be, you know, the number of atoms that will be destroyed in any given, that fall apart in any given moment of time, is the same. Okay. So you have all sorts of things, but free will, it's very, I have no idea what it means. That's the problem. So to say that it exists or not, Schopenhauer, by the way, had an interesting thing to say about free will, right? Yes, you are free to desire anything you want to desire, but you are not, how did he say? He said it much more beautifully than I can right now. But you cannot will what you want to will, you understand? So that's the thing about it. We can find the quote. I will find and I'll send it to you if you want to know. Okay, guys. So I believe the lesson for today is complete. Do you have any more we can read? Well, you can talk to me. I mean, you can read who knows where or when what, right? I mentioned the non-measurable sets in analysis, and I hope you will study it. There are such things that are very weird. They're called non-measurable sets. Okay, I can show you why they're non-measurable, and that has to do with the next lecture. We're going to talk about axiomatic approach to probability. Axiomatic approach is not as vague as what I described over here, but I do not see how the axiomatic approach relates to the meaning of probability, to the actual feeling of what it is. You understand? So you calculate the probability is 1/2. But what does the number 1/2 mean to you? Okay, we can be certain the number is 1/2, but have no meaning about this 1/2, or we can have some meaning about it and not be certain about whether it's true or not. That's the trade-off. Okay, so you can do both. So there, regardless, if you do it axiomatically, then there is no doubt that I can give you examples of things that have no probability. They always arise. Okay, they're called non-measurable sets, but in that context, I'm not entirely sure what they mean. And also for the purpose of derivation, if you want to understand the idea of where it comes from, this type of limit approach I found more useful. But I will show you the axiomatic approach on the next class. Sounds good? Just we'll do a little bit of it so we think why probabilities have this thing, and what you can base it on, and how the conclusions can be reached. Okay, guys. If you have any further questions, don't hesitate to stay. I will stop the video, and we'll be happy to talk to you more.